In this exercise, we want to find the domain, codomain, and range of a few different functions. So our first function assigns to each non-negative integer the least prime number greater than it. Okay, so first of all, what is the domain of this function? Well, this function assigns values to each non-negative integer. So the domain of this function is the non-negative integers, or as you might call them, the natural numbers. Now, what is the codomain of this function? What type of output does this function produce? Well, the values it assigns are prime numbers, right? And these are also natural numbers. So the type of value that this function will output is a natural number. So the codomain is also the set of natural numbers. Now, what is the range of this function? Remember, the range of a function is the set of values that the function does output, right? So this will be a subset of the codomain. In this case, this function outputs prime numbers, and in fact, it can output any prime number. Given a prime number, let's say p, if we apply this function to p minus 1, it will output p. So this function can output any prime number, and it only outputs prime numbers. So the range of this function is exactly the set of all prime numbers. Let's look at another function. Our second function is the function that assigns to each non-negative integer the largest integer not exceeding its square root. Okay, so again, this function assigns values to non-negative integers. So again, the domain of this function is the natural numbers. Now, what is the type of output of this function? So this function outputs the largest integer not exceeding the square root, right? So this will be an integer, and it will be a non-negative integer, since no square root will be less than 0. So the type of value that this function outputs is a non-negative integer, natural number. And finally, what is the range of this function? Right? What is the set of values that this function does produce? I claim that the range of this function is also the set of natural numbers. In other words, I claim that any natural number can be found as an output of this function. So, given a natural number n, if we apply this function to n squared, this will output the largest integer not exceeding the square root of n squared. In other words, the largest integer not exceeding n. So n. Since n is an arbitrary non-negative integer, this shows that the range of this function is indeed the natural numbers. Let's have a look at another function. Our third function assigns to each non-negative integer the number of digits between 0 and 9 that do not appear as decimal digits of the integer. So, for example, if we applied this function to the integer 101, now this includes the digits 0 and 1, so it excludes the remaining 8 of these integers, 2, 3, 4, 5, 6, 7, 8, and 9. So applying the function to 101, gives us 8. Okay. So what is the domain of this function? Now again, this function assigns values to each non-negative integer. So again, the domain is the non-negative integers, or the natural numbers. What is the codomain of this function? What is the type of output this function produces? Well, this function will output a number of digits, right? So this is going to be a non-negative integer. So again, the codomain will be the natural numbers. Finally, what is the range of this function? What is the set of values that this function outputs? Consider an integer. It must contain at least one of these 10 digits. And so this function cannot output a number greater than 9, right? And in fact, this function can output every number up to 9. So let's look at some examples. If we apply this function to the number 77, this includes one of the digits and excludes 9. So the function will output 9. Now if we look at the number 1,234,567,890, applying this function to this number will give us 0, since all of the digits 0 to 9 appear in this number. And it is not difficult to think of more examples that will give us every number between 0 and 9. So the range of this function is the set of non-negative integers between 0 and 9 inclusive. Let's look at one more function. Finally, let's consider the function that assigns to each pair of integers their difference. And we're considering the difference as the largest of the pair minus the smallest. Okay. So what is the domain of this function? Well, this function assigns values to each pair of integers. So the domain of this function will be the set of pairs of integers, which we know as a Cartesian product. What is the codomain of this function? So the output of this function will be an integer, since it's the difference of two integers, and it will be a non-negative integer, since we are always taking the largest minus the smallest, right? So the codomain of this function will be a set of non-negative integers, or the natural numbers. And finally, what is the range of this function? Now, I claim that the range of this function is also the set of natural numbers. To see this, take any number n from the natural numbers. Now we can apply this function to the pair 0, n, and this will output the difference between n and 0, which is n. Now, since n is just an arbitrary natural number, this shows that this function can output any natural number, and so the range of this function is the natural numbers. So in this exercise, we are just identifying some features of functions, right? These features are the domain, codomain, and range. Okay. So let's take a look at the first function. This is defined as the function that assigns to each non-negative integer its prime divisors. Okay, that is any prime number that divides the number evenly. Right. So for example, the prime divisors of 24. 24 is 8 times 3, which is 2 cubed times 3. So the prime divisors of 24 are 2 and 3. Okay? So the domain is pretty much given to us straight away, right? This function assigns values to non-negative integers. So the domain is the set of non-negative integers, or otherwise called the natural numbers. And the function outputs a set of prime numbers, right? So the codomain, this could possibly output any set of prime numbers, right? So the codomain will be the set of subsets of primes, right? And this we will write so the codomain is the power set of primes. Primes denotes the set of primes, right? So it's the power set of the set of all prime numbers. Remember, the power set is all possible subsets of this set. Now, what's the range? Well, actually, I claim that the range is also the power set of primes. Okay, so I claim that given any subset of prime numbers, any set of prime numbers, we can find a number such that this function will output that set of primes. Okay, so let's consider a set of prime numbers, right? What if you just multiply all the numbers in that set together, right? So you have a set of prime numbers, multiply them all together, and the number you get, well, it will have exactly those prime numbers in the set as its prime divisors, right? So this function applied to that number will give us exactly that set of primes, okay? So hopefully that's enough to convince you that the range of this function is also the power set of the primes. Our second function is defined as the function that assigns to each pair of integers the maximum of the two values, okay? So this function assigns values to pairs of integers, right? Remember, pair is just a Cartesian product, right? So the domain of this function is just the Cartesian product of the integers itself. Okay? Now, what's the codomain of this function? Well, it assigns the maximum of the two values, so it will output one of the two integers, right? So the codomain is a set of integers. And I claim that the range of this function is also the set of integers. Okay? To see this, consider any integer, call it n, right? Now subtract 1 from it, and consider the pair n and n minus 1. Right? Clearly this function will output number n given that pair, right? So hopefully I've convinced you that the range of this function is also the set of integers. In this exercise, we are asked to determine which of these are functions from the set of all humans to itself. Now remember, a function maps each element of the domain, the set of all humans here, to a unique element of the codomain. Again, in this case, the set of all humans. So let's look at A. Mother of X represents the biological mother of person X. Now, every person has exactly one biological mother, and so mother will map each element of the domain, each person, to a unique element of the codomain, a unique person. And so this is a function. B, we have parent of X, which represents a biological parent of X. Now each person will have a mother and a father, and so this will map one person X to two distinct elements of the codomain. And so this is not a function, since it does not map each element of the domain to a unique element of the codomain. In C, we have child of X, which represents the child of person X. Now, some people don't have any children, and so some elements of the domain will not be mapped to any element in the codomain. And also some people have multiple children. And so some elements of the domain will be mapped to multiple distinct elements in the codomain. Now, both of these are reasons why this is not a function from the set of humans to itself. And finally, firstborn child of X represents the firstborn child of person X. Now, certainly, if a person has a child, then they will have exactly one firstborn child. But again, there are people that do not have children, and so there are elements in the domain that are not mapped to any element in the codomain. And so this is not a function. And we're done. So we want to find the number of different functions going from the set A, consisting of two elements 1, 2, to the set B, consisting of three elements A, B, C. Okay? And then the number of functions going the other way from B to A. So let's start with A to B. So consider a function f going from A to B. Now, this function can map the number 1 to any of three elements, A, B, or C, right? And similarly, it can map the number 2 to any of three values, right? A, B, or C. And that covers all possibilities, right? So how many different functions can we find here? Well, 3 options for 1 and 3 options for 2, so that makes a total of 9 different functions, right? A function that gives the value A to 1 can take 3 different values for 2, similarly for mapping 1 to B and 1 to C. Okay, so how many are there from B to A? Well, let's consider another function. Let's call it G, going from B to A. Now, this time we can map the element A to any of 2 values, right? And similarly for B and C, each we can map to one of 2 values. So this time we have 2 options for the function to map A to, 2 options for B and 2 options for C, and that gives us a total of 8 different functions. In this exercise, we have 2 functions, f and g, defined from the set 1, 2, 3, 4 to itself, and our task is to find the composite functions f composed with g and G composed with F. Now let's start with F composed with G. Now to find what this function applied to x gives, remember we first need to apply G to x and then apply F to the result. So to find what this function will map 1 to, we first find what G maps 1 to. G maps 1 to 3, and then we apply F to the result. F maps 3 to 2, and so this composition will map 1 to 2. Okay, and for 2, first apply G. So G maps 2 to 2, and then F maps the result 2 to 1. And so the composition maps 2 to 1. G maps 3 to 4, and then F maps 4 to 2. So this will map 3 to 2. And G maps 4 to 1, and then F maps 1 to 4, and so the composition maps 4 to 4. So there's our first composite function done. Now let's look at G composed with F. So this time we apply F first, and then apply G to the result. So what do we map 1 to? Well, F maps 1 to 4, and then G maps 4 to 1. So this composition maps 1 to 1. F maps 2 to 1, and then G maps 1 to 3, and so the composition maps 2 to 3. Next, F maps 3 to 2, and G maps 2 to 2, and so the composition maps 3 to 2. And finally, F maps 4 to 2, and again G maps 2 to 2, and so the composition maps 4 to 2. And there are our composite functions done, and we're finished. In this exercise, we have 3 functions, and we will determine which compositions of any 2 of these functions are defined. So let's first think about F composed with G. Is this a defined composite function? Now, if we're trying to do this composition, then we are first applying G followed by F. So in order for that to work, we need the codomain of G to match the domain of F. And if we look at the functions, you see that the codomain of G is C, and the domain of F is A. So they don't match, and so this is not a defined function. Okay, what about G composed with F? So this time we want to apply F first, followed by G. Now looking at the functions, we see the codomain of f is b, and the domain of g is b. So they match, and so this is defined. So what is the domain and codomain of this composition? Well, again, we're applying f first. So the domain of the composite function will be the domain of f, a, and we then apply g. So the codomain of the composition will be the codomain of g, that is c. Next, we can write the graph of the function. So first, what does this composite function map 0 to? Well, we first apply f, which maps 0 to 0 plus 3, 3. And we then apply g to 3, and g maps 3 to 4 times 3, 12. So the first pair in our graph will be 0, 12. And secondly, what does this composition map 1 to? Well, first f maps 1 to 4, and then g maps 4 to 4 times 4, 16. And that is every entry in the domain. So that's the complete graph. And we could write the range of this function. The range is just the set of values in the codomain that are mapped to by this function. So here we have 12 and 16 as the range. Right, let's think about the next composition. F composed with H. So for this to be defined, we need the codomain of H to match the domain of F. So let's see what we've got. The codomain of H is A, and the domain of F is A. So yeah, this is a defined function. And it will have domain C, since that's the domain of H, and it will have codomain B, since that's the codomain of F. And again, we can write the graph of this function. So let's think about what different values of C will be mapped to. Well, H maps any even number to 0 and any odd number to 1. Right? And then we apply F. So if we are starting with an even number, then H will map it to 0, and F will map it to 0 plus 3, 3. If we're starting with an odd number, then H will map it to 1, and F will map that to 1 plus 3, 4. So this composition will map any even number to 3 and any odd number to 4. So here's how we can write this as the graph. So any even number, that is any number of the form 2n, for a natural number n, will be mapped to 3, and any odd number, that is any number of the form 2n plus 1, will be mapped to 4. And that's the complete graph. So what's the range of this function? Well, we are either mapped to 3 or to 4. So that's our range.
Next, let's think about h composed with f. Now, we would need the codomain of f to match the domain of h for this function to be defined. But looking at the functions, we see that the codomain of f is b, and the domain of h is c, so they don't match, so this is not defined. Okay, let's think about g composed with h. So for this to be defined, we need the codomain of h to match the domain of g. Looking at the functions, the codomain of h is a, and the domain of g is b. They don't match, so it's not defined. And finally, we'll think about h composed with g. So now we need the codomain of g to match the domain of h. And indeed it does. The codomain of g and the domain of h are both c. So this is defined, and we're applying g first. So the domain of this composition is the domain of g, that is b, and the codomain is the codomain of h, since we're applying h last. So the codomain is a. Let's think about the graph of this function. So g takes a number from the set b, 1, 2, 3, or 4, and multiplies it by 4. So let's start with 1. G takes the number 1 and returns 4. And then we apply h to 4. 4 is an even number, so h returns 0. So the composition takes 1 and returns 0. And g takes 2 and returns 8, which again is even, so h returns 0. And notice that whatever input we give to g, it will return an even number, right? Since it returns a multiple of 4. And so, in fact, whatever input we give the composite function, we will get 0. So we can finish this graph. Whatever value of the domain we start with, we will end at 0. Which also tells us that the range of this function is just the singleton set containing 0. And we're done.
In this exercise, we have two functions f and g, which both map natural numbers to natural numbers. Now our task is to find the composition functions f composed with g and g composed with f. So let's start with f composed with g. Now to find f composed with g of n, we find g of n and then apply f to the result. G of n is 3n plus 1. And now we apply f to 3n plus 1, which gives us 2 times 3n plus 1 plus 4. We're simply substituting this value for n in the definition of f, right? And now we can simplify this. And so we find f composed with g of n is 6n plus 6. Now let's do g composed with f. This time we're applying f first, so we find f of n, and then apply g to the result. F of n is 2n plus 4. And then applying g to this result will give us 3 times 2n plus 4 plus 1. And again, we can simplify this. And we get g composed with f of n is 6n plus 13. In this exercise, we have two functions, f and g, defined on the set of real numbers. And we want to define the compositions f composed with g and g composed with f. So let's start with g composed with f. Now, remember, in this case, we are applying f first, followed by g. So applying f to a value x gives us x squared plus 1. And applying g to this value x squared plus 1, using the definition of g, gives x squared plus 1 minus 2, which can be simplified to x squared minus 1. Okay, now let's do f composed with g. So this time we'll be applying g first, followed by f. So applying g to our value x, we get x minus 2. And applying f to the value x minus 2 gives us x minus 2 all squared plus 1. And this can be simplified to give x squared minus 4x plus 5. Let's find the composition of these two functions, f and g, right? F composed with g of x is what? Well, we first apply g to x and then apply f to the result, right? So this is f applied to g of x, right? Now g of x gives us cx plus d. And applying f to this value gives us a times cx plus d plus b. Now, suppose that this composite function is in fact the identity function. So the identity function maps x to x, right? So if this were the case, then we must have AC, right? A times C equals 1, comparing the coefficients, and AD plus B equals 0, right? And thus, rearranging these, we find that C is 1 over A and D is minus B over A.